Hello, this is NMR Unit 300. I have assimilated your instructor into my databanks. I will now take over. Oh, sorry about that. That happens sometimes. The NMR will get up with a mind of its own. That pesky NMR 300. Anyway, what we're going to do now is we're going to talk about how to start interpreting our spectra. So far we talked about instrumentation. Now, let's look at some spectra. Let's look at our spectrum, or actually our scale first. Let's start here. And so our NMR scale. So the NMR scale, it can go from, depending on what nucleus you're looking at, it can go from 0 to 12 ppm or 0 to 240 ppm. And remember, we're organic chemists, so we care about the protons and the carbons, and especially the protons. So a little bit about that scale, parts per million, which you might remember from general chemistry as a seldom used concentration unit. But here's where that comes from. So what we're looking at is what's called a chemical shift. So the symbol for this, this is where things show up on the spectrum. Does it show up here? Does it show up there? Does it show up here? That's called a chemical shift. And we say it's a shift relative to a reference compound. And the reference compound is called TMS, which is tetramethylsilane. So a little silicon chemistry here. Tetramethylsilane looks like this. It's a silicon with 3 methyl groups around it. And we use it a lot of times as a standard. So just about every sample that you run in an NMR has a little bit of TMS in it, or tetramethylsilane. And the machine locks onto that, and that sets it automatically as the 0 position there. And we look at all of our other signals in the molecule that we're studying, or analyte. We look at that relative to the TMS. And so that's our shift relative to our TMS divided by the total NMR frequency. Now remember, the NMR magnet is sending out this huge magnetic field, and magnetic field is correlated to frequency. And so what happens is that precessional frequency of the nucleus is doing this. So it's spinning around, and what happens is we hit it with a radio frequency, a strong radio frequency, and then it starts spinning around like this, and it relaxes like that. When it relaxes, it sends off its information as radio waves, and we actually pick it up with a radio antenna inside the instrument. So, but that's that precessional frequency. And when you're looking at one hydrogen versus another, those are small differences, very, very vanishingly small differences, and those amount to hertz differences. So our chemical shift, if something shows up here or here or here, those are differences in hertz, maybe 5 or 15 or 20 hertz. The magnetic field strength is measured in megahertz. And so what we're actually doing is we're dividing hertz divided by megahertz. Remember, mega stands for a million. That's where the parts per million come from. And the reason we do this is, remember, there's different types of instruments. You can have the Maserati of instruments, or maybe if your budget allows for it, the Cadillac of instruments, or the Ford Focus of instruments, or something like that. So different magnet field strengths will give you different shifts in hertz. But using ppm, no matter what instrument you use, on a 60 megahertz instrument or a 300 megahertz instrument, a 4 parts per million signal shows up at the same spot. So you're not going to have to constantly add in another factor here. So that chemical shift is a shift with respect to TMS, the compound that shows up at 0, divided by the total NMR strength. So it's kind of a ratio there, and we call it parts per million. So that's a little bit about our scale on the bottom there. And so remember, what's happening here is we're applying our strong field, and I'm using a little different terminology here. This is still a magnetic field strength. Some books will use H, some will use B as a symbol for the field. And so we're applying a strong field to our nuclei. And surrounding our nuclei, you'll have some electron density. Turns out when you hit that electron density with a strong field, it sets up its own electron current. So in that strong field, the electrons will start moving around. They set up their own counter field. It's called an induced field. The induced field usually opposes the applied field. And if you take the total of these, there's your applied field and the induced field, you get a slightly lower effective field. So here's where the electrons come in. The electrons actually act as a shield for that nucleus. The more electron density you have to bump up the field strength to get that nucleus to flip over. So we have our applied field, causes a current in your electron density. That current makes its own field. That induced field opposes the applied field, and then we have a slightly smaller effective field. What does this all mean? It means we can actually see different types of nuclei showing up at different spots on our spectrum because of the electron density. And so we're going to get a little bit more qualitative here. So we define an upfield and downfield on our spectrum. And so this over here corresponds to slightly stronger field strengths. So the field gets kind of stronger as you go from left to right. And that also corresponds to higher or lower electron density. So if you have your nucleus and it has lots of electron density around it, you're going to need a slightly stronger field to get him to flip over. And over here, you have less electron density around your nucleus. So if you happen to have a fluorine next door to your nucleus, it'll show up downfield. So we use it kind of as a left or right. You can say this guy's on the downfield side or the upfield side. And since we're talking about the electrons acting as a shield, the stronger shield is over here. So we call this shielded versus de-shielded. So here's a very shielded nucleus and a not so shielded nucleus. And so let's take a look at this. This is shielding. Chemical shift is what we're looking at right now. And so we're going to start off with something that's fairly shielded. And this is actually an NMR spectrum of methane, our simplest molecule out there, simplest organic molecule. And we're looking at what's called a proton spectrum. Right now we are looking at a proton NMR. So we're focusing on the hydrogens. And these hydrogens have electron density around them. And so for this guy, he's showing up right around 0.2 parts per million. So all of these hydrogens show up here and they give us what we call a singlet, a little single peak here. So that's for methane. Let's throw something electronegative on there. How about a chlorine? So here's chloromethane. So remember, chlorine is electronegative, so that electron cloud shrinks a little bit. So this is the electron cloud for chloromethane. For regular old methane, it was a bigger electron cloud. So having that chlorine on there, or chlorine is de-shielding things, the hydrogens now show up right around 3 parts per million. So an electronegative atom will cause a de-shielding effect. Chlorine is like, I'm sucking all the electron density towards me, and it pulls it away from the hydrogen. So the hydrogen signal shifts over, it gets de-shielded. It goes downfield. Let's throw another chlorine on there. Now we have dichloromethane. So now you have 2 chlorines pulling electron density off of those hydrogens. So the electron cloud gets even smaller now. Smaller electron cloud, we do more of a downfield shift. Now let's look at this next compound. Hey, why don't we throw 3 chlorines on there? And you may have been studying some of your nomenclature, so we'll talk about the name of this compound. And so when you have 3 chlorines on there, it really pulls most of the electron density away from this hydrogen. He has a really small electron cloud around him. He is de-shielded. Now, name of this compound, we saw methyl chloride or chloromethane. This is dichloromethane, or this one is trichloromethane. Also goes by a different name. So you could think, you might see this in some detective novels or some old-time movies. Someone might be sitting there doing a little work at the computer, and then as he's working on a computer, Some might sneak up and say, hey, where's that handkerchief coming from? Oh my God, it's soaked with chloroform. Someone's trying to kidnap me. That's what that is, chloroform right there. Also a common NMR solvent. So chloroform is used many times to dissolve our compounds that we're looking at. And so we actually see peak showing up here right at 7.2. That's where chloroform will show up. Now when we're doing NMR spectroscopy and we prepare a sample, we don't want to see this giant peak getting in the way of everything. So we actually replace it with this guy right here, deuterated chloroform. So that's deuterium. Deuterium is just heavy hydrogen. So hydrogen with an extra neutron on it, actually with and a neutron, so you got proton and neutron there. This one does not have a magnetic moment and does not show up in our spectra. So we use deuterated chloroform. But you always see a little bit of the regular chloroform that contaminates it. So let me show you another spectrum. This guy is, let's see, this would be diethyl ether. And that's the tiny bit of regular chloroform that's dissolved in our deuterated solvent. So this is called a deuterated solvent. So we use deuterated chloroform. That's not usually what a criminal will soak a handkerchief with to kidnap a victim, because it's way more expensive than regular chloroform. Got to be economical about these things. So now we have some trends here. So we looked at these compounds. Notice you have more electronegative atoms. You get some de-shielding going on. But we didn't look at 4-chlorines because then there's no hydrogen to look at, so that actually doesn't give a signal in proton NMR. You see a similar trend if you go from iodine to bromine to chlorine to fluorine. Look what happens to the parts per million. The more electronegative atoms de-shield those hydrogens more. And same thing happens with alcohols. Similar in electronegativity to chlorine, so they fall about the same region there. And so we have some correlations here. And just as with IR spectroscopy, we have a correlation table specifically for proton NMR spectroscopy. So let's take a look at that. So this is the proton NMR spectroscopy correlation table. And so we're focusing on what's happening to the hydrogen atoms, ignoring the other ones. And you have different ranges here. So here's some alkanes. Alkanes typically show up around 0.7 to 2 or so, usually not above that. And we highlight the hydrogen we're looking at. Here's a hydrogen that's 2 bonds away from an alkene. They show up around 1.5 to 2.5. Here's a hydrogen that is 2 bonds away from a carbonyl, usually around 2 to 2.5. Also happens if you happen to have an ester. These guys are similar. So 2 bonds away from a carbonyl, 2 bonds away from a carbonyl. Here's an interesting one that you'll see quite a bit of. Here's a hydrogen that's 2 bonds away from an aromatic ring. Shows up around 2.5 to 2.7. And you'll notice there's some overlap there, so we can't get too much information from just the correlations here like we did with IR. So you do have to take some of these with a grain of salt. You can't just say, oh, there's something at 2.5, so it must be near a carbonyl. No, because it could also be near a ring. So keep that in mind. There's a lot of overlap, especially in the shielded part of the region. But I'm going to show you some of the more interesting things to look for. Here's an alcohol OH. One thing we notice with IR spectroscopy, when you have something that can hydrogen bond, that causes a signal to widen. That happens on NMR spectroscopy as well. And it also causes the ranges to get pretty big. Depending on how much water is present in your sample, an alcohol OH tends to show up anywhere from 0.5 to 5. Covers half of the spectrum there. If you have a phenol, usually around 4 to 7, but it can vary. And let's see, we also have regions for where hydrogen near an iodine shows up, or a bromine. And you can see the effect of the increasing electronegativity. Here's a really common one. If you have a hydrogen 2 bonds away from an oxygen, say in an alcohol, an ether, or an ester, those almost always show up right around 4. Something to look for. Let's see, if you happen to have a vinyl hydrogen, this would be a hydrogen that is directly attached to a CC double bond. These show up around 5 to 6. Not much else shows up around there. So if something shows up between 5 and 6, you do want to start thinking alkene. Another really important one, 7 to 8. If something shows up between 7 and 8 parts per million, 99% of the time you can say benzene ring. That takes care of 6 of your carbons. Between 9 and 10, aldehydes usually show up there, but not much else. And the most downfield thing we tend to see is a carboxylic acid proton. That shows up around 11 to 12. And so we actually get a little bit of information from our chemical shift. And what can cause some of these shifts? We looked at electronegative atoms, but when you have alkynes and alkenes and aromatic compounds, these guys set up their own little magnetic fields that will actually affect some of the shielding. So alkynes show up around 1.5 or so. Alkenes show up around 5 to 6 parts per million. They set up their own magnetic field because of the pi electrons, and that usually reinforces the applied field, and so it acts to de-shield things a little bit, and it reliably puts those protons right between 5 and 6, which is good. It tells us there's an alkene there. For aromatic systems, you can draw aromatic compounds a couple different ways. And remember, you can draw it with the alternating single and double bonds. But remember, you got resonance. So we picture these electrons circulating around. So that's why sometimes you'll see the aromatic circle. It's good for looking at symmetry and things like that. And so if we put this guy on edge, we have these electrons circulating around here. So think of a donut of electrons. It's around dinner time for me, so I'm starting to think about donuts, good healthy dinners here. So we have this donut of electrons. They set up their own magnetic field, which really helps to reinforce the applied magnetic field. That causes a de-shielding effect. That causes things like benzene to show up around 7.2 parts per million. So there's different things that will cause shielding and de-shielding. And so this is chemical shift is what we're looking at here. And that's one of the pieces of information we get from NMR spectroscopy. The next thing we're looking at is number of signals. So here's a spectrum. It has 2 signals. Got one here, got one here. Turns out the number of signals is equal to the number of types of hydrogens that you have in your compound. And if you're looking at carbon NMR, it's equal to the number of types of carbon. Again, useful piece of information, another piece of our puzzle. So let's take a look at ethane. Ethane, you've got 6 hydrogens. All of them are pretty much in the same environment. If you look at this hydrogen, he is attached to a carbon, and that carbon is attached to another carbon. Same for this hydrogen, and this one, and this one. So they all show up at the same spot. And it's 0.8 parts per million here, so pretty well shielded. Benzene, look at him showing up right about 7.26 parts per million. Every hydrogen is actually in the same environment. There's really no difference between them. They're all attached to an aromatic ring. In fact, let me draw this a little bit more symmetrically. So there's your benzene ring. It turns out the more symmetry you have, the fewer signals you'll have. So there's a plane of symmetry here, and here, and here, and here, and here, and here. Very symmetrical compound. Every hydrogen shows up at the same spot. There's only one type of hydrogen here. Now we've got 2 types. Because let's take a look. This guy's methyl acetate. And we have a CH3 group right here, and a CH3 group over here. And when we're looking at these, get in the habit of labeling those hydrogens. So notice we have an asymmetrical molecule. So these hydrogens, I'm going to label them as HA, are 2 bonds away from my oxygen. These hydrogens are 2 bonds away from a carbonyl carbon. That's a different chemical environment. These guys are experiencing different things. There's no difference between this HB and this HB, but there's a difference between this guy and this guy. And you just count the bonds. 1, 2 bonds, you hit oxygen. Over here, 1, 2, 3 bonds, you'll hit oxygen. So HB is going to be more shielded. HA is going to feel the effect of those oxygens more. 2 types of hydrogen, 2 signals. Useful piece of information there. And if you look on your correlation table, you'll see this is the type of hydrogen that will show up between 3.5 to 4.8. And this is a type that will show up around 2 to 2.5. Let's take a look at another one here. And we're just going to look at numbers of types of carbons and hydrogens. And you can pause at each new structure and try to figure it out yourself too. See if where our answers match. So try pausing, writing down your answer, then unpausing. But let's look here. We've got carbon next to bromine, carbon next to a carbon next to bromine. There are 2 types of carbon. There will be 2 carbon signals. Let's look at our hydrogens. There's hydrogen that's 2 bonds away from bromine, or 3 bonds away from bromine. 2 types of hydrogen. Let's look at this guy, an ether. So we have a couple hydrogens here, which are in the same environment as the hydrogens over here. And then we have these hydrogens which are a little bit farther away from oxygen. So any difference will show up on an NMR. And so we actually have 2 types of hydrogen right here. And also 2 types of carbon. The carbons that are next to oxygen, the carbons that are farther away. So 2 types of hydrogen, 2 types of carbon. Now let's look at this guy right here. This will be an isomeric ether. So same exact molecular formula, but I just move the oxygen over. Now things change. This guy actually has 4 types of hydrogen, 4 types of carbon. Here's why. Let's look at the hydrogens. You have this hydrogen here, we'll call him HA. He's on a methyl group next to oxygen. Then you have this guy, we're going to call him HB. He's on a CH2 group next to oxygen. But he's also next to a carbon. That's a different environment. You'll get a different signal. Then this guy over here, HC, he's on a carbon who's attached to 2 other carbons. Different chemical environment. Then finally HD, he's on a methyl group that's pretty far away from oxygen. So you're going to get 4 hydrogen signals in your spectrum. And 4 carbon signals as well. Compare that to what we saw here. 2 types of hydrogen, 2 types of carbon. So with NMR, you could tell a difference between these 2 ethers right away. You can say it's ether this one or ether that one. Let's look at something aromatic here. So this compound right here, we have 2 chlorines. And we've got 4 hydrogens. Turns out, if you look at any one of these hydrogens, they're all in the same environment. They're all next door to a chlorine. This hydrogen is experiencing the same stuff as this hydrogen. And you have a lot of symmetry here. There's a plane of symmetry here, plane of symmetry right there. You have 1 type of hydrogen. If you look at carbons, you have the carbons that are next to chlorine or a little bit farther away. So you actually have 2 types of carbon. Let's get rid of some symmetry. Now I'm going to have a chlorine and a bromine. Now this hydrogen is no longer the same as this one. So we'll call this A, we'll call this B. This hydrogen and this one, these guys are in the same environment. These guys are in the same environment. So now we have 2 types of hydrogen. And we have 1, 2, 3, 4 types of carbon. Remember, we still have a plane of symmetry running through this molecule. So symmetry is important. The less symmetry you have, the more signals you will have. So that gives you a nice piece of information there. Let's really get rid of the symmetry. Now we've got how many types of hydrogen here? Pause and count them up. You should have come up with 4 types of hydrogen because we don't have a plane of symmetry anymore. We've got a chlorine and a bromine. Here's a hydrogen that is 4 bonds from chlorine. This guy is 5 bonds away from chlorine. This guy is 5 bonds away from bromine. This one is 4 bonds away from bromine. There's 4 types of hydrogen here. And there is no symmetry other than a flat plane of symmetry on this molecule. And so every single carbon is actually different as well too. On the carbon spectra you will see 6 signals showing up. 6 types of carbon. So number of signals is important. Let's look at a couple other examples. A couple more ethers. And so in this case we've got how many types of hydrogen? That's right, 3 types of hydrogen and 3 types of carbon. So there's your 1, 2, 3 types of carbon. And we go over here, 3 types of carbon, and I'll leave it for you to figure out how many types of hydrogen you get. So pause it, write it down, write down how many types of hydrogen, unpause, and did you come up with 4? Because that is the answer. Here's something interesting about alkenes. If we look at these hydrogens over here, you have free rotation about this bond. So these hydrogens all kind of experience the same environment. They're all about the same distance from that oxygen at some point because they're spinning around all the time. You don't have free rotation about a C-C double bond. And so what that means is this hydrogen is different than this one. Because this one is always cis to oxygen, this one is always trans. You got 2 signals on that same carbon. Then you have this type of hydrogen, then you have HD over here. So you actually have 4 types of hydrogen. Alkenes will tend to give you more signals than you expect. A little bit more complexity there. And if you're looking at even a compound like this, you actually have 1, 2, 3, 4, 5, 6, 7 types of carbon here. Because, those carbons are farther and farther away from that bromine. They feel the effect of that bromine a little bit less. And when you look at types of hydrogens, 1, 2, 3, 4, 5, 6, 7 types of hydrogen technically. Now in practice, sometimes when those hydrogens are real similar to each other, they'll kind of squish together on the spectrum. And the 60 megahertz won't be able to separate them out, but maybe that 1 gigahertz spectrometer will be able to do that. But what we were looking at is the number of types of hydrogen here. So 2 pieces of information are really important. Now let's look at our next piece of information, the area underneath our signals. That's going to give us some information as well. Turns out the size of those signals is proportional to how many hydrogens cause them. A bigger signal means you have more hydrogens causing that signal. That's useful. So let's take a look at an example right here. And this guy right here, I'm going to give you the formula and we're going to figure this guy out. Out of the 20 or 30 million known organic compounds out there, we're going to use these 2 peaks to figure out what this compound is. Think we can do it? Oh, you're skeptical, huh? Well, guess what? We're going to do this. We have enough NMR knowledge to do this. We do need one piece of information, though, the molecular formula. This guy is C8H10. And where we get the molecular formula, we don't just pull it out of the air or anyplace else. We get that from the combination of a mass spectrum and an elemental analysis. So we need those 2 pieces of information. So you don't go into this with no information. Someone who's worked, with NMR for years might be able to look at the spectrum and say, I know what that is. But we're going to deduce it, and we're going to be systematic about it. I'm going to show you how to figure this out. This is a logic puzzle here. So here's where the size of these signals come in. We look at the area underneath the signals, and we don't look at the signal height. Signal height doesn't tell you much because sometimes you might have a wide short signal or a tall narrow signal has the same area. So we actually have to calculate the area. And the spectrometer will do that for you. Some spectrometers will put a little number in down here and you can get a ratio. Really advanced ones will tell you how many hydrogens are there. That takes a lot of fun out of it. But we're going to look at what's called an integration line. And you can see the bottom and the top of these integration lines here. And this is an expansion of the signal. An integration line goes up when it hits a signal. If there's more hydrogens causing the signal, it goes up a little bit higher. And here's what's cool about that. So I'm going to draw a line through the bottom of that integration signal. And I'm going to draw one right up here as well. And I'm going to put one right here. And remember, we're looking at the integration line, not the height of the signal. Very important. And I'm going to make a hydrogen ruler, a custom-made hydrogen ruler. If you have the spectrum in front of you on a piece of paper, you can do this with a sticky note the same way. And notice the spacing here. This spacing is not the same as this spacing. So I'm going to throw in another line, and there you go. I have a hydrogen ruler in units of hydrogens. And so when I look at this one right here, this one went up 2 units. This signal went up 3 units. Remember, there's the top of my integration line right there. So we're looking at the top and bottom of these steps. And what I end up with is I can say, well, there's a 2 to 3 ratio. That's useful info right there, 2 to 3 ratio. 2 to 3, though, that's the same as 4 to 6. That's the same as 20 to 30. That's the same as 2,000 to 3,000. So which is it? This is where we go back to our formula. We know we have 10 hydrogens. We will pick the ratio that adds up to 10. So now we know that there are 4 hydrogens in this environment. There are 6 hydrogens over here. That's useful information. Then we say, hey, wait a minute, I've seen stuff showing up right here. That's between 7 and 8 parts per million. Let's take a look at our handy correlation table. 7 and 8 parts per million. That's where aromatic hydrogens show up. So these 4 hydrogens have to be attached to a ring. So we're going to do a little counting here. We have a piece of our puzzle. And so if you have 4 hydrogens on your ring, that means you're going to have 2 substituents, because you have hydrogen, 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 and hydrogen. Let me draw those in for you. And you'll have 2 things that are not hydrogen. Remember, we have 6 spots on these rings. And so you can have those two substituents next to each other. They could be a little bit farther away or a little bit farther away. Those are your 3 possibilities for that puzzle piece. And here's our accounting. We're going to say that we just did something with 6 of our carbons and 4 of our hydrogens because of this signal. That only leaves 2 carbons and 6 hydrogens. There's not too much you can do with those 2 carbons and 6 hydrogens. In fact, you need to make 2 methyl groups. So I'm just going to subtract those out. I've used up all my atoms. So here's my puzzle. I have 3 pieces to my puzzle. I have to have an aromatic ring and 2 methyl groups. And I put that piece together, and I will end up with either this compound, or this one, or this one. Out of the millions of compounds out there, we're down to 3. That's pretty nifty, I think. But we're like, well, which one is it? We can tell. We can tell by remembering that the more symmetry you have, the fewer signals you'll have. So let's look at this compound right here. This guy has a plane of symmetry that runs through here. And so we have the CH3 hydrogens, the guys next to CH3, and the guys a little bit farther away from CH3. Proton A, proton B, proton C if you'd like. That's 3 types. We've only got 2 types, so we cross him out. Let's look at this one. This one has another plane of symmetry. So we have a hydrogen here, hydrogen here. These guys are in different environments. This hydrogen is in between 2 methyl groups. This guy is as far away from the methyl groups as possible. These hydrogens are next to the methyl groups. And then we have the CH3s. That's 4 types of hydrogen right there. Here's our compound. All of these hydrogens on the ring in this compound are in the same environment because we have a plane of symmetry running right through it. The CH3 groups are also in the same environment. There's a plane of symmetry this way. This is the only compound that will give you 2 signals. That's our compound right there. This is called p-xylene. This is a common organic solvent. And what you'll see is you have 2 types of hydrogen. We have the methyl hydrogens. Okay, let me point them in the right direction. And we have the aromatic hydrogens showing up here. So we used 2 signals to figure out this compound. Pretty cool. But it basically is a logic puzzle. You want to put these puzzle pieces down. Let's look at one more example so we can look at this phenomenon of peak area. And it's sometimes what's called the peak integration because the instrument will actually integrate the area underneath those peaks. And so if you ever hear me talk about the integration of the signals, I'm talking about that peak area. And so here's a compound, has a couple of major signals. This guy right here, I'm going to point this out, this is actually a little bit of our residual solvent right here. This is acetone with some deuterium in it. Some compounds dissolve better in acetone than chloroform. So we're going to ignore the solvent peak. But we're not going to ignore these other 2. And notice we've got those little integration lines right there and there. And there's the bottom of the step. So we'll make our ruler, and notice what we have here. We actually have a 1-to-1 relationship there in terms of the spacing. So this guy is 1 unit high. This one is 2 units high. This is a 1-to-2 ratio. And so this compound happens to be called hydroquinone, and your phenols are showing up right here. That's these 2 hydrogens labeled HA. Then you have these 4 hydrogens showing up here. So this is actually a 2-to-4 ratio. And usually when you have these solvent peaks that you have to ignore, if you happen to see them integrated, a lot of times what gives them away is the integration will be like really, really tiny right here. So if you have like a 4-to-2 ratio and you have something that's integrating for like 0.001, then usually know it's a solvent. Or the spectroscopist may point it out and say that's your solvent. So that's a little bit about the peak area. And so already we're starting to get a lot of information from these peaks from this NMR spectroscopy. But I'm going to show you how you can get way more information. But one last thing I'll leave you with this spectrum here. Remember we have these OH, that's for phenol, which shows up around 4 to 7. This is showing up around 7.5, actually 7.8 or so, 7.7. Those hydrogen bonding groups can really show up all over the place, so you have to be careful about them. They're sneaky that way. So, next up I'm going to show you what happens when hydrogens are next to each other.